In this video, I'd be talking about introduction to algorithms. Um, yeah, so well, I have an input. I feed the input to the algorithm, and I expect an output. So the algorithm processes the output. They process the input to give me the output. Now, an algorithm could be a correct one or an incorrect one. The correct one is the one which halts and produces correct output to specific input. Now, um, the input provided to an algorithm is called an instance, right? Incorrect algorithm it is an algorithm which is not a correct algorithm, and even incorrect algorithms could be useful if their error rate could be controlled. Now, some algorithms are classified as NP-complete. So these are the algorithms which, some problems are called NP-complete because there's no efficient solution that has been found yet, nor it has been proven that an efficient algorithm could exist for those problems. If proven for one, and these are actually those kind of problems, they belong to a certain class in which if you prove that an efficient algorithm exists for one problem, then it applies for, or it could be proven for the rest. Or if you could at least come up with if you could come up with an efficient solution for one, then and prove that it is the most efficient solution for that problem, then efficient solutions for other problems could also be found, right? Now okay, so okay, what do I mean by analyzing an algorithm? So say for example, if I'm providing an input to an algorithm, I analyze my algorithm based on the time that my algorithm takes in order to convert the input to output. Also the memory needed in the process. Might even talk about the communication bandwidth, if the network is involved. Now, when you analyze an algorithm, you'd come to know that it's not just the size of the input that matters, it's also the type of the input that matters. So if I talk about, say for example, insertion sort algorithm, then not just the size of the input that matters, it's also the way the input is organized. So I could have, say, 100, or say, I don't know, like 10,000 numbers that I'm trying to sort, and all of them might be already arranged in the order that I want them to be sorted in. So insertion sort wouldn't have to do as much work as it would have to do if the input were to be in reverse order. So so it's not just the size, but also the way the elements are arranged, or the type of the input that matters. Now consider consider two algorithms, the one with 2n square one with 2n square instructions needed to process an input of size n to give a correct output, and another one that needs to execute 50 into n log n instructions to process the same input size n to give a correct output. Right. So yeah. So if you compare these two here, there will be a crossover point. That is, for less values of n, 2n squared is actually less than 50 n log n. So for less, or for n less than the crossover point, you need 2n squared instructions to process the input to get the output, and you need 50 n log n instructions to process this input here to the output. It's the same input, by the way. So for n less than crossover point, insertion sort is performs good because 2n square is less than 50 n log n. That is, you need less number of instructions in the insertion sort to process the output than the merge sort. Okay, but for sufficiently larger n's, that is for n greater than the crossover point, um, 50n log n would be less number of instructions to process the same input than 2n square, right? So for n greater than the crossover point, merge sort is much better than insertion sort. So just to put things in perspective, let's actually solve it. And to make it more dramatic, say your insertion sort is running on a computer which can execute 10 power 9 instructions per second, and your merge sort is running on a computer which can execute 10 power 7 instructions per second. So this one is slower than this one. Now remember, insertion sort is running on a faster computer, so in order to process an input of size n is equal to of size 10 power 6, that is n is 10 power 6, insertion sort would have to execute 2 into 10 power 6 squared instructions, which would take, because the computer can execute 10 power 9 instructions per second, it would take the computer 2000 seconds to process 2 into 10 power 6 square instructions on input n of size 10 power 6. Now the merge sort, the computer executing the merge sort on the same input of size 10 power 6 would have to execute 50 into 10 power 6 log 10 power 6 instructions to process the input. And because the computer can execute 10 power 7 instructions per second, it would take this computer 100 seconds. So if you could notice it, right, despite of the fact that this was the fastest computer, it took 2000 seconds to process the same input size, right, and the same size as well as the same type, so that's the same input. Now this being relatively slower computer took just 100 seconds to process the same input. So performance of algorithms really matter. If you could read through this, algorithms are the core of most technologies used in contemporary computers. It is at larger problem sizes that the differences in efficiencies between algorithms become particularly prominent. Having a solid base of algorithmic knowledge and technique is one characteristic that separates the truly skilled programmers from the novices, right? But with modern computing technology, you can accomplish some tasks without knowing much about algorithms, but with a good background in algorithms, you can do much more. Thank you.